we were talking about bifurcations. We had talked about the saddle node bifurcation. It's the main one. Today, we'll talk about two more bifurcations and then summarize them and then discuss their robustness. Last time, we did the saddle node, and kind of the picture to have in mind there is if we have some parameter r, and here's x, we'll have a parabola kind of opening to the side, and one of them will be stable and one of them will be unstable. One side of the critical point, the bifurcation point, in this case, let's say r equals 0, there's no bifurcation, there's no equilibrium points, and on the other side, there's two of different stability types. So that's the one that we went on and on about last time. And now we'll go on and on about a couple more. Another example of bifurcation has a different type of normal form, and it's called the transcritical bifurcation. It has other names. Remember what a normal form was? That's kind of the prototype. We're looking in 1D, so for the one-dimensional vector field will locally look like this. The normal form for this type of bifurcation is x dot equals rx minus x squared, where again, r is our bifurcation parameter and x is our state. So it looks like that. And if you were to plot the vector, this vector field for r negative, r equals 0, and r positive, you'll get an idea of what happens. So here is, let's plot the three, plotting x dot versus x. What if we start with r less than 0? For r less than 0, this looks like a parabola. It has to pass through 0. Notice this is x, r minus x. So that means x dot has to equal 0 at 0. So this will be a, I'll do it in a different color, a parabola opening downward by passing through 0. Okay, so we would have a fixed point at 0 and a fixed point here. If we use the approach of seeing what direction is x moving. Remember, when x dot is positive, it's moving to the right. X dot is negative, it's moving to the left. So we would have that this point, the left side point, is an unstable point because the arrows are moving away, and x equals 0 is stable. Let's say x star equals r. If you solve this x dot equals 0, x dot equation, set it equal to 0, and what do you get? You get that there's 2, 0, and x star equals r. 0 is always an equilibrium point for this case. And if you think of that, like, where might this happen? Population dynamics. If there's no population, it's not growing, so it's an equilibrium point. So here we have those two are equilibrium points. Now, when r equals 0, then we just have x dot equals negative x squared. We can plot that. This is for r equals 0. This will just be a parabola opening downward that intersects, just touches the x-axis at 0. So there's only one point. What direction are things moving? Over here, they're moving that way. Over here, they're moving that way. So this would be what we might call a half stable point, but it's really unstable. And then, so here we have what, x equals 0 is the only equilibrium point. And then what about r greater than 0? What do we get for that? So this will be a parabola, again, opening downward, so concave down. Now it's on the right side, so it's going to be looking something like that. It intersects 0, so we've got a point, fixed point there, fixed point here. Let's plot the arrows that tell us the direction the flow is going. That one's incorrect. Going this way. So again, the one on the left is unstable and the one on the right is stable. And this is x star equals 0 and x star equals r, because it just always has to be. But in this case, r is positive. So if we were to summarize this with a bifurcation diagram, so let's do a bifurcation diagram. And sometimes the transcritical is called the TC, but it has another name that maybe it will make sense after we plot this. Remember that what a bifurcation diagram gives us. We plot where is the location of an equilibrium point as a function of the parameter, in this case, r. For r less than 0, 0 is a stable point, so we'll make that solid. And after the bifurcation point for r greater than 0, x star equals 0 becomes unstable. So I'll put a dashed line. So that is the x star equals 0. The other equilibrium point is looking up here in the upper right. It's x star equals r. So that just means it's a straight line, slope 1 before the bifurcation point. So for r less than 0, that's an unstable point, and then greater than 0, it's a stable point. So that would be our diagram. And remember what our convention was: solid line equals stable, dashed line equals unstable. So the two branches of equilibrium points exchange stability. So this is sometimes called the exchange of stability bifurcation of the two branches. So that's a bit odd, but that's how it goes. We'll just look at a simple model of a laser. So a simple model of a laser is that you've got, I don't know if you've taken optics. You have this, I did, but I don't remember how lasers work. You've got a mirror on one side, this like half mirror, but also lens on this other side. You pump in energy. This is an active material in here, meaning if you give it energy, something will happen, stuff will light up. And out of this will come laser light. Things actually bounce around in there, and then you get, laser light. And the nice thing about lasers, right, is the beam it's not spreading out as much as most light. There's a simple model for this, which is a kind of a population model of the number of photons inside the laser. Our variable that we're going to care about is n. N could change with time, is the number of photons in the laser. And the way that n changes, so we'll write differential equation, n dot equals, it's the gain minus loss. The gain comes from excited atoms inside the active material that interact with the photons. And that will produce more photons. So that's where things will be gained. And then loss is photons escaping through the lens. There's a couple of parameters that go into this. One of them is, we'll call it capital N. This is the number of excited atoms. It would be related to kind of the density and the volume inside that active material part of the chamber. And that's a constant. And then there's something called the gain coefficient. It's related to how the atoms get excited. This number of excited atoms is, of course, a real number that's greater than 0. And this is a greater than 0. So the gain part that I wrote up there, gain equals G times N times little n, the number of photons. There's a time scale related to how the photons exit through the lens. We could write that. Loss through lens is related to a time scale, 1 over k. K is the parameter that we'll use. So it's a time scale for photons to escape. We've written as loss will be equal to negative k times n. Remember, it's a simple model just to sort of get at things. I may have said the number of excited atoms is a constant. It's not. You can have n be capital N be a function of time. If we do n dot equals gain minus loss, this is going to be G n n minus k n, which doesn't look too exciting. It's just linear n. But big N, the number of excited atoms, is related to little n, the number of photons. And this is a simple model for it. Capital N is constant n naught minus alpha n. So that's where we'll get a quadratic term. And please don't ask me about the details because I'm no laser physicist. So if you plug this in, we'll get G n naught minus k n, a linear term, minus alpha g n squared. And what is this alpha? Alpha is the rate at which atoms drop to the ground state. Ground state is like the unexcited state of an atom. So now we've got something that looks interesting. It looks like x dot equals rx minus x squared. You could rescale things, okay? So it looks like that. It looks like the transcritical normal form. So we expect a transcritical bifurcation for the laser. And just the transcritical bifurcation depends on the sign of R. And in this case, what is R? R is is related to this sign of G n naught minus K. Another thing that's different about this is, right, the number of photons, it has to be a number greater than or equal to 0. We can't have any state, including equilibrium points, that have negative n. So if we were to look at the situation described by this, we could just plot n dot versus n for different cases of the sign of g n naught over g n naught minus k. We'll write this in terms of n naught. Okay, so we'll look first at the case of n naught minus k over g and plot n dot versus n, but reminding ourselves that we can't have negative n. We'll just kind of hash that out. Then our plot will be, maybe I'll use red, make it easier. It'll be a parabola, looks like that. And this right-hand side point is the only equilibrium point, n equals 0 is a fixed point and it's stable. That means if there was some kind of perturbation or something that made the number of photons greater than 0, it would be the dynamics of the system drives it back to 0. The middle case would be n naught equals k over g. And again, we could plot this. N dot versus n. Hashing out the right side, but keeping it because we learned to plot with that. We've got a parabola that touches the n axis. And so we have this equilibrium point here that we might call half stable. This is the bifurcation point, because what's going to happen after this? Well, we hopefully have an idea. So here's n naught greater than k over g. What do we get? We get a parabola opening down. As you change this parameter, it's like you're pivoting this parabola about the origin. So now it's pivoted to this side so that n equals 0 is a fixed point, but it's unstable. And then we have an equilibrium point that is greater than 0. So things are kind of being driven there. We have now n equals 0 is unstable. And then here's this other one, n star greater than 0, stable. There's some fixed point. We could solve for what it is. Right now, I'm just trying to give you qualitatively. Okay, so this is what we expect for the bifurcation diagram for the laser. We can plot n naught, and this will be n star. The bifurcation point happens at k over g. Before that, we've got that 0 is a stable point, and there's no other points. And it's kind of like there's this ghost equilibrium point that comes out of nowhere and kind of shoots up there. That's what it'll look like, since there's nothing allowed down here, right? There's no n star less than 0. And the n star equals 0 equilibrium point becomes unstable. So if we were to kind of plot, kind of sketch what the dynamics does, that's it. So this is the bifurcation diagram for the laser qualitatively from this simple model. So that means you need a critical number of atoms in the ground state. Yeah, I guess I didn't say what n naught is. Need a critical number of atoms n naught. And this is, n naught is equal to number of atoms in the ground state, the lowest energy state of an atom that could get excited. So you need a critical number of atoms n naught for the laser to operate. Before that, so I guess we could say in this region, this is not a laser. And then up here, it is a laser. It won't operate like a laser. It's a coherent beam. All right. So that's just you could look at the book if you want to see more, or even the original paper from 1983 with this simple model. This just gives you an idea. So that's the transcritical bifurcation.